And also, let me share my screen again. All right. Okay. Now we understand that the system is working in this condition, and the second order approximation is working. What we did was three main steps. The first step was finding the k and sigma and omega d of where we are. Then we calculate the steady state error of the current uncompensated system, and also we calculated the third pole of the system to see that second order approximation is okay or not. So such thing is happening until now. Now we want to add some compensator to the system in the form of k k s plus a, s plus very small value, let's say 0.1 over s to the system. What happens is if we draw the root locus of the system again, we will get 1 here, 0.1 here, minus 1, minus 2, minus 10. This time here is root locus, here is root locus, and this one is root locus, minus 10, minus 2, minus 1, minus 0.1, and 0. And we know that this is something happening again with the system. So we have the root locus in this form. This time, I know that the zeta should be again 0.174 because we don't want to change the transient response, okay? In this case, again, step 1 is saying step 1 is k, nu k, s plus 0.1 over s, s plus 1, s plus 2, s plus 10 should be equal to minus 1, and tangent minus 1 on omega d on sigma should be equal to some theta, in which cosine theta is 0.174. From this, again, three equations, three unknowns, we can find that omega d is minus, omega d is 3.837, sigma is minus 0.67, and k is 158.2. So what I'm understanding is a prime, the change in the thing is here is 3.84. This point is like minus 0.67, and the k here is 158.2. You see that the values that we had before were like for the old system, k was 164 and omega d was omega d was 3.92 and sigma was minus 0.694. You see that the transient response from A point to A prime has changed very slightly. Of course, the K value changes completely. Not completely, it changed a higher value. It's 164 to 158. So the change is big, but about transient response characteristics. Zeta is the same, that is overshoot is the same, omega d is the same, and we can say sigma is the same. So in this condition, the system is working with this pole, the closed loop poles are here, and this one is here, and this can be found as minus 1155. So how do we find that? We say K of sigma plus 0.1 over sigma, sigma plus 1, sigma plus 2, sigma plus 10 is equal to minus 1. So from here, and I know that K is already 158.2. From here, sigma will be minus 11.55. So I find the system with a new condition. And what is this is the compensated system. What is the new error now? I know that the error this time is limit of K G compensated, G equal to, which is Kp. Okay, this time it's equal to infinity because I have 1 over s in the transfer function, feed forward transfer function. When s goes to 0, this means that the steady state error becomes 1 over infinity becomes 0. So steady state error goes to 0, and the transient response is not affected. So if I see the system, ideal integrated compensated is going to 0 with steady state error going to 0. Why? Because if you plot this line from 1, because you have the input here, okay, 1, and you have you see that what has happened in the steady state is like you had the old steady state error like here. Now it is 0. It is completely gone. And if you check the transient response, you see that it is not that much affected. So what are our observations here? The observation 1, steady state error old was 0.108. Now steady state error new is 0. Second, transient response is not affected that much. So with PI controller, ideal integral compensator, we can guarantee these two things. Transient response is not affected that much, and steady state error becomes 0 as the type of the system increases. Any question? No question? So why we are calling this PI controller is shown here. It is like we have the integral part and proportional part. So GS of C is proportional part plus integral part, which is like S K1 S plus K2, which can be also rewritten as, if you get a factor from K1, you will get S plus K2 over K1 over S. So this is also equivalent to K S plus A over S. This means that K2 can be bigger than K1 to make the A very small. So we have the integration part and proportional part And if it is shown as a zero and pole addition in the origin, it's because of when you sum them up, they can be written in this form. Otherwise, they are just one integrator and one proportionality part. Any question? No question? Okay. Now we say that because the ideal compensators are expensive, so in the ideal form, we have something like this. This is the ideal form. In the non-ideal form, which we call lag compensator, we say instead of doing this, simple passive networks can create something like this, which is minus pole of the compensator and minus Z of the compensator, as shown also here in figures labeled as C down there. So adding some zero and adding some pole, but not on the origin, but close to origin. What is happening here is that if you, first of all, we can understand that the transient response is not affected, okay? The transient response is not affected. So what we see here, one, transient response is not affected. But second, why ESS decreases? Because we are not increasing the type of the system. In the ideal one, we were increasing type of the system. Here, we are not increasing type of the system. We are just holding the type of the system as it were. But what is happening to steady state error? Let's see. For this system, if I calculate KV, let's say old, I can say it is limit of SGS when S goes to 0. And it becomes like K product of ZIs over product of PJs, okay? KV old. Now, what about KV new, which is limit of SG of compensation and G of old when S goes to 0? This becomes K product of ZI over product of PJ multiplied by ZC over PC. Okay. What does it mean? It means that if ZC is like 0.2 and PC is like 0.1, 0.2 over 0.1 is 2. So what is happening is like KV old is increasing to KV new. So by ratio, I don't have, let me write it down here. By ratio ZC over PC, the KV value increases. This means that steady state error is 1 over KV, and this means that steady state error is decreasing. So what do we see here when we are comparing the integral form, pure integral form and non-pure integral form, is that in the pure integral form, if you increase the type of the system, you are definitely decreasing the limited steady state error to zero. But in the lag form, in the non-ideal form, you are just decreasing the steady state error. You are not definitely making it zero, okay? And also transient response is not affected. Why again? Because you're adding zero and pole at the same time. You have the character of zero pole cancellation, so it is not affecting the transient response. Clear? No question?
Yes.
Okay. Now, what happens to steady state error? I discussed it, but I can say it again, like to make it completely clear. It is like G old is like product of S plus Z I's over product of S plus PJ's. And let's say the system is first order. So I just find the type 1 system, not first order, type 1 system. So KV is, let's say, calculated as limit of SGS. When S goes to 0, it becomes KP of ZI over pi of PJs. And G nu is S plus Z of compensator product of S plus ZI over S pi of S plus PJs multiplied by S plus PC. So this means that KV here becomes limit of SG nu. S goes to 0, it becomes K product of ZI over product of PJs multiplied by ZC over PC. And I know that ZC over PC is always bigger than 1 because I'm using Z this way, P this way, Z this way. Always Z over pi in the absolute value is bigger than 1. So KV new is always bigger than KV old. This means that steady state error new is always less than steady state error old. So this is happening to the steady state. And why the transient response is not affected? Again, if you can see the A figure, we can say point P is on the root locus because theta 1 minus theta 2 minus theta 3, it is 2k plus 1, 180 degree. But here we have minus theta of pole C plus theta of ZC minus theta 1 minus theta 2 minus theta 3 is also equal to 2k plus 1, 180, because theta PC is close to theta ZC. So in the lag compensator, if you are choosing to add the pole and 0 close to origin, you have to also make sure that these two pole and 0 are also close to each other so that the transient response is not that much affected. If you put them away from each other, zero pole cancellation becomes weaker, and when zero pole cancellation becomes weaker, the transient response will be affected so much. Not like the example before. Here the affection was not that much. You see 3.92 comes 3.84, and 0.69 comes 0.69 again, 0.67. Okay, so this effect be small means that your zero pole cancellation, the zero here is 0.1. You can change it with 0.01 also to see what is the effect of the condition. Okay, now we have an example. We want to do it the same for this one. It is the same system, so I won't give all the details, but we want to use lag compensator to see what happens. We know already that the system is like this. We found and show why the system is like this. So this is the current working condition. What are important for us is K is 164.6, omega D is 3.926, and sigma is 0.694. Based on these, we can find what is the settling time now, what is the peak time. The overshoot is known also. We can find the steady state error as shown here, 0.108. So for the working condition, we can calculate settling time, peak time, and overshoot is given here, but we can calculate other values. And we are using the second order approximation. It worked good. It's okay because the third pole is on the LHP, okay? Now, I'm adding a lag compensator like this. So as you can see, Z of the 0 is about 0 of compensator is 0.111. Pole of the compensator is 0.01. Okay. So the new system is like G new or compensated is equal to K S plus 0.111 over S plus 0.01, S plus 1, S plus 2, S plus 10. This is our new system, okay? Again, for this system, I have to start with K, so let's say Kg is this. Kgh is equal to 1. I can find that tangent minus 1 of omega d on sigma is 100, like a theta, in which theta is cosine of zeta. Sorry, cosine of theta is zeta. Cosine of theta is zeta. So from here, it says that K is 1581 and omega d is 3.836 and sigma is 0.678. Okay. Now the system is working here and here and here, the third pole, and also we should have a fourth pole. Okay. Where is the fourth pole? It's like between these two lines. If I make it bigger, like I have this point to this point like this, and the third pole is here, and again zero pole cancel, the fourth pole is there, so zero pole cancellation is happening because zero is not changing its place. Zero of the open loop and zero of the closed loop are at the same point always, so they are there. What happens to the steady state error this time? Let's see. This was for Kp, yeah? Kp is limit of Kg when S goes to 0 will be 1581 multiplied by 0111 divided by 0.11 multiplied by 2 multiplied by 10. This becomes approximately 79. So steady state error becomes 1 over 1 plus Kp, which becomes 0.0125, which is smaller than 0.108. So all the steady state error this time is decreased, but it is not going to be zero, definitely, because we are using cheaper integrator instead of using ideal integrator. So if we sum up the thing, we can say that our uncompensated system was like this. Our lag compensated is adding the 0 at 0.111 and adding a pole at 0.001. The K's values are different, Kp values are different, E infinity values like this, they have decreased. Dominant second order poles are these, we call these dominant second order, means the third and the fourth pole are can be ignored because of zero pole cancellation or because they are on the LHP left hand half plane very left. The third pole is found like this. The fourth pole there is none, but here we have the fourth pole, and the zeros here is none, here is 0.111. Okay, and we see that the response is given now about the unity step response. If I draw the one here, you see that this time error decreases, but it does not become completely zero. We have some error here, the same error there. But the transient response is also not that much affected. It is affected more than the ideal case, but it is not that much affected. Also, we can discuss the thing that different type of Z and P can be considered. How? We know that in the Z over P, we had, for example, 1, 1, 1, 0 over 1, 0, 1. It is about 10. So it is 10 times increasing the Kp. And also we can have Z on P in the second compensator example. It's like 0.11 over 0.01. It's about, again, 10 times. This means that you can use the other zero endpoints with trial and error. The thing is, the steady state errors becoming better does not change that much, but the transient response can be much more affected. Okay, the transient response can be changed, much more affected. Okay. Any question? Now we want to see how can we improve the transient response via cascade compensation. We discussed the steady state error with ideal and non-ideal ones. Now we want to see that how we can improve the transient response. The transient response is generally gets better if we do the gain adjustments from the past week on the root locus. But if we want to go to a point that is not reachable on the current root locus, we have to add zeros and poles to the system such that the root locus behavior changes. And the change in the root locus behavior is to guarantee that zero is the addition of this zero is causing the root locus to pass through the point that we want. And it is done by ideal compensators, derivative compensators called PD, and they can be also in the non-ideal form called lead compensators. So, the transient response of a system can be selected by choosing an appropriate closed loop pole location on the S-plane. If this is on the root locus, then a simple gain adjustment is that all is required in order to meet the response specifications, as I discussed. But if that point is not on the root locus, we have to add some zeros, single zeros, to the system in the feed forward. So we can say, based on PD, compensator transfer function is z plus some z of the compensator. So this is adding some derivative with some proportionality to the system. Differentiation is noisy process in terms of mathematics, so it requires active circuits first of all, which is expensive, and also it's a noisy process, which we can discuss next. Let's see how we do that. The thing is, this is really based on trial and error, okay? Really based on trial and error. Assume that we have such working condition, okay? And we want to we have such working condition, and we want to do this. We want to keep the overshoot the same, and we want to increase the system speed. Means we want to decrease the peak time, and we want to let's say decrease the settling time. So peak time is pi over omega d for second order approximation, and this means that we want to increase omega d. So increasing omega d means with overshoot constant means I have to move in this way, okay? Moving in this way means I need a point here. So gain adjustment is not possible to move from the A point to B point because B point is not already on the root locus. What do we do is to add some zeros to the system such that the point B is reachable. Example 1 on B says, if I add S plus 2 to the system in a cascade form, G of C, the root locus changes from the old one to new one, such that it passes through the point that we want. Okay? It passes through the point that we want. In this condition, the TS has decreased very good. Okay. Another example says if I add S plus 3 as the compensator, such thing happens to the root locus. Again, I can pass through a better point on the root locus that has higher higher omega d. And if I add G of C S plus 4, I will have another condition, another response, another type of the root locus, and I will get to a point with higher omega t. Now let's see what is happening to the system in these cases. So I'm adding a 0 at -2, a 0 at -3, and a 0 at -4. So dominant poles are changing definitely because the place of the A point is changing. K is changing. So we know how to find these dominant poles and Ks, yes, from previous examples. Zeta is the same, okay? You see zeta is the same because we are moving just on one zeta line. So omega n is increased, as you can see. In all cases, different values of increment. Overshoot is the same because we are moving on the one line thing. Settling time has decreased, sorry. You can see the system has become faster. Peak time has decreased again. The system becomes faster in terms of response. Kp is increased, and E infinity has decreased. And third pole, here we have none. It's a pure second order. It is very nice to do it. This is second order approximation. Second order approximation good because we have the third pole at a good place. Any question? No question. And you can see that the steady state error has become better because our input is 1, and the steady state error has become better. So this is input. Steady state error has decreased. And the system with different zeros, they can have almost the same overshoot, but they have become faster in terms of T peak has decreased. So in the lead compensator, what we are going to do is, again, improve the transient response via cascade compensation. But this time we are not going to use pure, just a zero, okay? Just a zero. What we are going to do to say that lead compensator, GC of S, is equal to S plus Z. So this is pure zero, but we don't want pure zero. We add some integrator to the system also, P of C. So this is lead compensation. You see that this is very similar to the lag. In the lag also we had S plus ZC over S plus PC in the lag. So difference is in the lag we have something like this. We add the zero and pole here, in which Z on P is bigger than. But in this case, in the lead one, what we want to do is add, it is the lag and lead name is because it's one of them is lagging the system, the other one is leading the system. So it is in the lead part of the left hand side. You can remember like this, and this is pole, this is vice versa, mirrored like that, and this is the zero of compensator. So if this is called lag compensator, this is the lead effect. Let's see how is this lead compensator is affecting the system's response in terms of and why is it good? The first thing is it doesn't need power supplies. When compared to the ideal one, it is non-ideal because it can be done with passive networks, and also noise is reduced because we have differentiation, but integration is reducing the noise effect. So in that terms, it gets better even when compared to the ideal PD when we are using lead. What is it exactly doing is like when we don't have the lead compensator, we have like theta like theta 5 minus theta 4 minus theta 3 minus theta 2, okay, plus theta 2 is not 180. It means that for this system, okay, with 1, 2, 3. Sorry, theta 2 is not there. We have just theta 5, theta 4, and theta 3 is not 180 because desired location is not on the root locus. What we do, we say that we have a desired point here. We choose that point and then we find theta c. How? We say theta 5 minus theta 4 minus theta 3, okay, plus theta 2 minus theta 1 should be 180, so that the desired point is on the root locus. In this condition, what I'm finding is theta 2 minus theta 1 is equal to 180 minus theta 5 minus theta 4 minus theta 3. So I find theta 2 minus theta 1. This means that I am finding the theta c, theta of the compensator, this theta here. So according to this theta found, I can choose nu 0 and nu pole and put it on the system such that the root locus of the system passes through the desired pole. So we will see examples about this again. Let's now sum up our thing. We have PID controller like this. So we have, if we want to both improve the steady state error and transient response at the same time, for the transient response, this is PD for transient response. This is PI for steady state error. So this is called PID controller. If we want to do it step by step, which one should I do? For example, I want to make better the steady state error and make better the transient response. Make better means I design it such that it goes through the specification that I need in terms of transient response. Which one should I do first? PD or PID? PI, sorry. PD or PI? Which one should I do first?
PD.
PD. Yeah?
Yes.
PD, yeah, PD should be done first. Why? Because when we are doing PD, we first fix the transient response, change the system, and so it comes first. We change the transient response, we do what we want about the transient response, then we go to PI part and make the steady state error 0, while not affecting the transient response. Because if I do the PI first, then fix the transient, fix the steady state error, then I do the PD. In that case, the transient response will be, deteriorated, and the steady state error may increase from the 0 again. So first we do the PD, then we do the PI. And about the lag lead also, first we do the lead, then we do the lag, okay? First lead about the transient response, then we do the lag about the steady state error. So these are the things that you're going to do in your final project. All the 8 steps here should be seen on the final project. And also all 8 steps should be reported in the final project Okay, so as a summary, we see that PI controller is like S plus Z over S. Lag is S plus Z over S plus P. PD is pure, just S plus Z. And lead is S plus Z over S plus P. Again, you see lag and lead are the same. But the difference is like, let me show the difference again here. This is like this way. This is like this way, okay? And this is the PID. So we have S plus Z, S plus another Z over S, and we have S plus Z over S plus P, S plus P. We will see, you will see it in so many examples inside the book. And also the examples we will have next week. Okay, this is not putting this just this way. Now we want to see when we say we want to add zero or add pole to the system, what does it mean? If we are using active circuits, one of the examples were operational amplifiers that we studied in the second lecture or second week of the course. You see that if I'm using active controller for this and I'm choosing Z1 and Z2 as like resistors and capacitors, I'm getting the G of C, which is the compensator transfer function. For example, R2 on R1 is a pure gain. It is like acting a K1. 1 over RC over S, it is like pure integration. It is like K2 over S. And RCS is like differentiation. It is like K3S. So when we say we are adding a K, we are adding a K over S, or we are adding a KS, they have all physical meanings that can be added to the controller part of the system. Or in terms of active, we can continue like this. You see PI controller, this is equal to somehow K S plus A over S, yeah? So this is a PI controller. This is somehow equal to K S plus B, let's say. This is a PD controller. And PID controllers and lag and lead controllers and their combination are like this. All of them can create the desired compensators. The thing is, we have to choose Z1 and Z2 and put it here, Z1 and Z2 here, and we will get the G of C like this. So in each of the case, we can use what we are doing to add these zeros and poles to the system. About passive circuits, but as you can see, we don't need any amplifier. We don't need operational amplifier, but we can choose simple networks like with a input voltage to output voltage before the input to the previous controller part or the plant part. You can add this. So adding this is also meaning that, for example, this is equal to K S plus A over S plus B. You can see that pure integration is not possible here. Yeah, you don't have 1 over S. This is also somehow K S plus A over S plus B. And this is also K S plus A like S plus C over S plus B, S plus D, which is lag lead compensator. You see that these passives are just able to do lag lead and lag lead. We don't have the possibility to show PI, PD, or PID here because they are using passive circuits, okay? Now we have an example to solve. We will solve this example to see that how we can solve the problem with given the system below. Design the system such that it can operate with a peak time that is 2/3 that of the uncompensated system at 20% overshoot, and with 0 steady state error for a step unit. Okay, we will solve this problem. Let's have 10 minutes of break and then we will continue, okay?